So I'd like to introduce Hugh Holbrook. Hugh Holbrook, my apologies. I think about Hal, the movie star, right? So Hugh is the Chief Development Officer for Arista Networks. He is responsible for their AI and their cloud platforms and systems software engineering. He's also been the chair of IEEE Working Group for the standardizations of source-specific multicast, and currently serves on the steering and technical advisory committees for Ultra Ethernet Consortium, which is here to talk about this morning with us. Hugh, we look forward to your talk on enhanced Ethernet usage for both AI and high-performance computing. Please welcome Hugh.
Thanks, Steve.
Forward, back.
Great.
All
Thank
right.
you. All right.
Buddy.
So thank you, Steve, for that nice introduction. Thank you all for coming. It's really an honor to speak to you all here, illustrious community doing super important work. Thank you for everything you do. Hopefully, today I'll share something that I've been pretty involved in for the last several years. Since it's hard to believe, less than 2 years ago that GPT-3 and ChatGPT kind of dropped on the scene. Feels like it's been a sea change since then, but there's been certainly a tremendous amount of interest in AI and networking for AI among my customers. Over the last several years, I've been quite involved in the work of the Ultra Ethernet Consortium, trying to make networking for AI and HPC better and do it on top of Ethernet and IP. So with that, I'm just going to jump in. So what is the problem that the Ultra Ethernet Consortium is tackling? Like, why do we need a new look at networking for AI and HPC? Well, specifically, it's that AI and HPC traffic is a little bit different from traditional internet data center traffic that you might be used to. The endpoints are super fast. They're designed to generate traffic really fast. The picture on the right of the screen here is the Grand Teton server from Meta. It's an OCP design that they contributed to OCP. It's got 8 GPUs in it. This will saturate wire rate at 400 gig on all the ports, like nonstop. AI traffic has a small number of flows, typically, that are high bandwidth. They can, like I said, they can saturate the link. Typically operates in a data center environment where the round trip times are pretty short, so we're not talking WAN traffic. This is 10 microseconds or so within a data center. And then the nature of the traffic, and I'll talk more about this, is distributed computations. And the distributed computations have the characteristic that it's a whole bunch of independent GPUs that are working together on a problem, so they start sending simultaneously. And that is very demanding on the network because it's very bursty and simultaneously bursty across the whole network. And then compounding this whole thing, the completion times of these computations, many of which in sequence make up a job, are determined by the slowest flow or the slowest participant in the computation. And all of this put together combines to mean that sort of vanilla networking or normal networking that we're used to doesn't work so well for AI and also HPC. So the Ultra Ethernet Consortium was started around 2 years ago to address this problem. And put kind of succinctly, it's trying to make Ethernet better work really well for AI and HPC use cases. The Ultra Ethernet Consortium was founded by the 10 companies at the top of the screen here. That is a mix of operators, equipment vendors, systems vendors, with experience in AI, networking, and high-performance compute. Since then, there have been over 100 companies that have joined, many of which are listed here on the slide. There are 1,300 participants, individual people like us participating in it since then. So it's become a fairly significant movement in the industry. The Ultra Ethernet Consortium is a standards body, so anybody can join with a legitimate interest. It's a JDF project. It's composed of many different working groups. The 4 working groups listed horizontally are the initial working groups that started out in the Ultra Ethernet Consortium. Since then, there have been more that have been added. The product of the Ultra Ethernet Consortium will be a spec, kind of like IEEE 802.3 or something. It's going to be a single spec initially. The 1.0 spec will probably have somewhere close to 800 pages in it. So it's a big specification that will cross many different layers. We expect it'll probably release early next year. A kind of guiding principle of Ultra Ethernet and the Ultra Ethernet Consortium is that RMA, or remote memory access, is really critical to good performance. Like any accelerator, a GPU, TPU, XPU, what have you, that's out there today is communicating primarily using remote memory access with other GPUs. And remote memory access, very simply, is just hardware delivery straight to and from memory. So packets come in off the network and they're DMA'd straight where they go in memory. Packets come out of memory and they're DMA'd straight into the network with bypassing the kernel with minimal copies. Hardware is involved, typically the network interface card, doing loss detection, retransmission, loss recovery. The common implementation of RDMA over IP networks today, this is also done over InfiniBand, but over IP networks today is Rocky. You might have heard of Rocky or Rocky V2, which is RDMA over converged Ethernet. And it's widely used today and it's pretty dominant. So RMA is a great concept and is really essential to performance of AI and HPC applications. The Ultra Ethernet Consortium believes that Ethernet and IP on top of it are the right foundation for RMA. For all the reasons that are, I'm sure, obvious to you all, there's a broad ecosystem of equipment, of vendors. You can get NICs, switches, optics, cables from many different people. It's multi-vendor at all layers. It has a proven history of innovating rapidly from 1 to 10 to 25 to 40 to 100 to 200 to 400 to 800, 1.6, 3.2T are all on the roadmap. There's lots of tools for operations, management, testing. Scaling is proven, and it's widely understood. Like, people understand IP, they understand Ethernet. There's plenty of books. People learn about it in school. So the Ultra Ethernet Consortium is building Ultra Ethernet on top of Ethernet, fundamentally. RMA, like I said, is really important, but we feel that it's important to revisit RMA and specifically revisit Rocky. So RMA as a concept, like I said, totally great. Like no issues with RMA, like absolutely required for good performance. But the protocol that RMA is widely deployed on today is, has its roots in the InfiniBand Trade Association and is probably around 25 years old. In the late 90s, the RDMA protocol ran on top of InfiniBand and was standardized then and has since been ported to run on top of UDP and IP and Ethernet underneath. But it's lacking some things that we feel are pretty important. In particular, multipathing, which I'll talk about a decent amount about why that's important. The reliability mechanisms, it uses go back N reliability, so when a single packet is dropped, all packets after that are dropped. The congestion control algorithm, we feel like we've learned a lot in the networking community in the last 25 years about congestion control, and we can apply some new techniques in this multipathing environment that can improve things. The scale requirements of these AI networks are just going up and up and up. And then security has only gotten more and more important, so we're integrating security into the protocol. So again, RMA is fantastic, like no issues with RDMA. It's just a specific implementation of RMA on top of Ethernet that is prevalent today that the Ultra Ethernet Consortium is taking a look at revisiting. So core to this is the Ultra Ethernet Transport, which is a transport protocol, sort of a sibling of TCP and RDMA at some level in the protocol stack, that has a lot of fine attributes, and I won't list them all here on the screen, but I'll talk about many of them later in the talk. But the goal of the Ultra Ethernet Consortium is to preserve the applications that run on top of the transport, preserve the IP and Ethernet layer that runs below the transport, improve it in various ways, and extend it as necessary above and below. But then significant work is happening at the transport protocol to improve it for these AI and HPC applications. So I just want to show you a picture here on the screen, just to put your head in context of where all this stuff happens in the network. So the AI and HPC applications are taking place inside data centers. So this is a picture of a typical AI data center, which I'm sure many of you are familiar with. that has GPUs, which are kind of the central component, GPUs or TPUs or accelerators in the middle along that blue line. And so these are racks with servers in them, as I've got it depicted. And there's a back-end network above and a front-end network below. So the front-end network is your traditional data center network that does storage, compute, WAN access, management, telemetry, configuration, like all that kind of stuff. The training, the inference, the super high bandwidth GPU to GPU communication is happening in what's typically called the back-end network. The back-end network, the protocol is almost exclusively RMA that's running across the back-end network. These are very high speed. Next year, today it's 400, next year it'll be 800 gig per GPU. These are short RTT networks, kind of 10 microseconds, 150, 200, 300 meter lengths. The front-end network is a more traditional network that has TCP, NVMe, RMA, SNMP, lots of different stuff running on it. These are more like 100 gig per endpoint, and it might extend into the WAN, so it might be slightly higher RTT. So in the back-end network, there's two kind of subnetworks that people talk about. There's a scale-up network, which is the network that connects the GPUs together at very high speed. So it might be 8, 10, 12 times the speed of the scale-out network. And so this is connecting GPUs together in tightly coupled domains for things like tensor parallelism. And then the scale-out network is the thing that connects 10,000, 100,000 GPUs together into a cluster so I can run very large, say, training jobs or very large HPC compute. And the scale-out network is the domain of UEC, at least the 1.0 version of the UEC spec that'll be coming out. So that's working on the scale-out network. We might, in the future, consider scale-up, and there's interest in that, but today it's scale-out. So where this all happens, just zooming in on an XPU server to just kind of set your thoughts on the place on the place where this is happening. An XPU server today, commonly has like 8 GPUs inside it. It's got a scale-out fabric, a switch inside it that might be Ethernet, it might be NV switch, it might be something else that interconnects the GPUs at very high speed, and then each GPU is connected to a network interface card that's connected to the scale-out network. So the server contains both the scale-out and the scale-up network inside it. And I just want to point out that the NICs play a very important and kind of central role. The network interface cards an important role for Ultra Ethernet because this is where a lot of the Ultra Ethernet transport implementation is happening. Like at these speeds, packets are arriving, every 40, 80 nanoseconds on the wire. You can't do it in software, so you need hardware acceleration. So this is where hardware offload and the remote memory access is actually happening, is in the network interface cards. There's a lot of acceleration happening there, so they play an important role. So I want to look at a network layer diagram and just talk to you about what the Ultra Ethernet Consortium is doing at all the layers. I can't bring myself to talk about a 7-layer ISO model, so this is a 4-layer IETF model with application, transport, network, and link. So at the application layer, or more specifically at the kind of boundary of the application and the transport layer, is the Ultra Ethernet Consortium is defining libfabric APIs. And I'll talk a little bit more about this, but this is essentially modern APIs that support RMA. And it's kind of more rich semantics than BSD sockets that is tailored for HPC and AI. At the transport layer is the Ultra Ethernet transport protocol. And this is, like I said, the core of what, to some degree, like probably where the most effort in the Ultra Ethernet Consortium is happening. And it's broken into different layers: semantics, packet delivery, security, reliability, congestion management. Together, these are all forming, a protocol that does RMA, multipathing, out-of-order delivery with integrated security. And I'll talk more about that later. IP sits underneath it, so it's all built on top of IP, v4 or v6. Vanilla IP is all you need to run Ultra Ethernet protocols. There are some extensions that we're defining, one specifically called packet trimming, which can improve things in some environments, and I'll talk more about that. And then, despite the fact that it's called Ultra Ethernet, you might think, oh, they're redefining Ethernet and making a lot of changes because it's Ultra Ethernet. It's actually just plain old Ethernet. So what's changing is the layers on top of Ethernet. So it's just plain old IEEE Ethernet. We have defined some extensions. One is link layer retransmit. And I'll talk about that, which can improve things in some environments, but you can be a completely compliant Ultra Ethernet switch by supporting just Ethernet as it is today. So I want to talk now about load balancing, which is a really important problem, and I want to spend a little time on this because it's a significant problem for AI traffic, and I want to give you a sense of why this is so important, and because it drives the kind of core design decision of the Ultra Ethernet transport. So I'm just going to tell you something which I'm sure you all know about flows and packet ordering, but just put this in front of us. Today, networks keep packets within a single layer 4 flow in order. Like, why is this? Because the transport protocols, TCP and RDMA, don't do well with out-of-order packets. So out-of-order packets are interpreted as loss. So if I see 1, 2, 3, 5, I assume that 4 was lost immediately. Lost packets, if they happen repeatedly, are interpreted as congestion, and they cause the transport protocol to slow down. So the well-understood wisdom in the industry is don't reorder packets within a flow. This is a diagram, I won't spend any time on it, but it's just like a TCP congestion window diagram. When TCP sees 3 duplicate acts, it cuts the window, which is effectively the transmission speed, in half, and then backs up from there. So how is this implemented? How do networks keep packets within a flow in order? Well, they do hashing typically. So the 5 tuple of the source and destination L4 ports are fed into some kind of hash function in hardware that computes a number, which is then mapped to an interface. And the interface is one of the ECMP paths to get to the destination. This works really well if there are a lot of flows, but it's harder if there are not so many flows. So I want to look into this and spend just a few minutes with some kind of simple math on how well flow hashing does for AI and HPC networks. So here's a scenario that I want to talk about. It's a rack with a single top of rack switch and 32 GPU servers connected directly to it. And then the uplinks of this top of rack switch are connected to 32 spine switches. There's 32 uplinks and 32 downlinks, so it's like fully provisioned, no oversubscription. Every GPU is generating K flows out of it. And I'll look at 2 scenarios, one with a lot of flows and one with not so many flows. And just for the sake of this example, I'll assume that all the flows are leaving the rack. So there's no east-west communication within the rack. This is a distributed computation mostly going on with neighbors outside the rack. And then I'm doing flow hashing across all of the spines. That keeps the packets in order. And the question is, how many flows do I have on each uplink? And so I want to look at that question and just kind of run through some simple math or simple experiments that show this. So here's a picture of the average utilization. So this is a probability density function. So this is showing you the probability of how many flows on any given link. And this is for that scenario that I just showed you, and I'm assuming 80% offered load. So across all the GPUs, every one is say 100 gig GPU, and each of them is simultaneously generating 80 gig worth of traffic in 1 gig flows. This is 80 flows coming out of every server. So you see the peak here, of course, on average is 80, right? Because it has to work out that there's on average 80 flows per uplink. No link actually gets oversubscribed until it gets more than 100 flows. And that doesn't happen very often. It's often that little tail there on the right of the picture that there's some small number of links occasionally get oversubscribed. So I get 99.95% throughput on average, which is really great. This is like, data centers today are like built on top of this. It works really well. What if I told you that AI traffic has not very many flows per port at any given time? So what if I said, well, instead of 80 flows, what if there are only 8 coming out of a GPU? So this is that same diagram, the same simulation I ran, but this time only with 8 flows per port. Again, this is 80% utilized, so any given uplink is saturated when it's got more than 10 flows that map to it with that vertical line there. So you can see that, again, this is still working pretty well. That tail of fraction of the time that some link has more than 10 flows mapped to it is a little bit larger, but it's still not very oversubscribed when it happens, and it doesn't happen that often. So I'm still, on average, getting almost 97% efficiency. So of my 80% utilization, I'm like doing 77 77% actual throughput, which is pretty good. And I think most network operators would be mostly okay with this. But now I want to look at a slightly different metric, which is the maximum utilization, which is like how overloaded is the worst case link coming out of my top of rack switch. Not just on average, but how bad is the worst link? And so of course, on that last slide, you can see there's a small chance that I'm more than 10, but what's the chance that one of them is out there? Well, it's actually pretty high. So this diagram shows you that on average, the worst link will have 14 flows mapped to it, which is 140% of the traffic that it can carry, which means that the worst link is actually only 70% efficient, or 71% efficient in the worst case. So and so I'm looking at the maximum utilization here. Same picture as the last one. So on average, I'm still 97% efficient. But the worst case link is only 70% efficient. So why am I dialing in on this so much? Well, it's the nature of distributed communications that happen in AI and HPC. So AI and HPC is made up of collective communications. And these are distributed computations from MPI that you might have heard of as things like reduce and scatter and all gather and broadcast. And these are doing things like averaging and broadcasting the gradients at the end of a training step. Or they're implementing a distributed matrix multiply and summing up partial products across some number of GPUs into a final matrix. And these arrange some number of GPUs, and it can be pretty large, 32, 64, even 1,000, into some kind of a structure like a ring or a tree. So think about what happens if I'm doing a ring computation with, say, 32 GPUs or 16 GPUs like is shown here. And data is flowing all the way around the ring. So the computation isn't done, in fact, until the data circulates through the ring twice. Well, I'm taking data from my upstream neighbor, mixing it with data that I've got locally, and then passing it along to my downstream neighbor. That computation is running at the speed of the slowest link in the ring, because I can't do anything until I've received the data from my upstream neighbor. So the whole computation runs at the speed of the worst case link. And that doesn't matter whether it's a tree or a ring, and both of them have the same fundamental property. And that is really important. So an individual slow link is really bad. So the question is, I started out by saying, well, networks never deliver packets out of order. But what if they could? What if you just said networks could deliver packets out of order? What if they could send packets from a single flow and spray them across all of the uplinks? So here's that same worst case diagram for a scenario where I take a 1 megabyte transfer, which is going to be composed of 256 4K packets. And then if the packets are actually sprayed across all of my 32 uplinks. And again, this is an 80% utilized scenario, and I look at how much utilization each link gets over the lifetime of that transfer, which is at 800 gig, about 10 microseconds. Well, in this case, an individual link is only exceeding its capacity over that window of time if I've got more than 256 packets in that 10 microsecond period. The worst case utilization, if I'm spraying packets, hovers around 90% of capacity if I have 80% offered load. It's dramatically better. So if with 80% offered load, my worst case falls to 90% typically. And so there's a very, very small number of times where I cause any link to be oversubscribed. So on the whole, even for an application driven by the worst case link in the entire computation, I'm still 99.98% efficient. So this is why packet spraying is so important. But of course, like I said, TCP and sort of vanilla RDMA don't do that well. And they don't handle out of order delivery, which brings us to the Ultra Ethernet transport, which is trying to address that problem fundamentally. So the Ultra Ethernet transport is a transport protocol that enables packets to be delivered out of order. And this is sort of a key tenet. And sort of like very simply, I mean, spraying is easy. Delivering packets out of order is easy. It's what do you do on the other side when they arrive out of order that's the tricky part. And so the Ultra Ethernet, just from a delivery standpoint, the Ultra Ethernet transport really simply just tags packets with their ultimate destination. Those packets, when they arrive, are matched to a buffer, and you just DMA them straight into memory based on a tag in the packets. It's pretty simple. So it's at its core, the Ultra Ethernet transport is just doing RMA when packets arrive out of order. But this creates some challenges for the network if I'm doing packet spraying. One is just path selection and congestion avoidance. I no longer have one path from source to destination. I'm using many paths, or ideally all of the paths in the network. And so I need to create entropy in my packets so that the network can spray the packets across all of the lengths. And a kind of key problem that just doesn't arise with TCP or standard transport protocols is the fact that I can have congestion in the middle of the network that might affect just one path, or I can have congestion at the end point on the way to the destination host that affects all the paths of a flow. And I need to distinguish those two, and I would like, ideally, to avoid using paths in the middle of the network that are congested and just move to a different path. And if the end station is congested, I need to slow down, because there's no way to avoid it. I just need to slow down. And there's a kind of some interesting challenges about picking enough entropy so that I can avoid a path quickly and be able to slow down. So that's one problem. A second problem is detecting losses in an out-of-order delivery protocol. So if I'm spraying packets across all the uplinks, then they arrive not necessarily in the order I sent them, because the links have different lengths, because there can be variable amounts of queuing delay on the way. So I send packets, and then they're arriving in some random order, and I can no longer do the thing where I say 1, 2, 3, 5 means that 4 was lost. So networks generally detect detected losses through either timeout or out-of-order packets, as I just described. But with packet spraying, out-of-order arrival is no longer really well defined. And timeouts are made harder because I would like in these short RTT networks to have tight timeouts so that I can detect loss, request retransmission quickly so I don't delay my protocol. But I would like fast timeouts, but fast timeouts are made complicated by the fact that there isn't a single round trip time. There's different queuing delays on different paths, different speed of light delays. So I need new methods to detect loss and to recover from it in this protocol. So one solution that I alluded to before that is actually kind of at the IP layer to this loss detection problem is called packet trimming. And this is not a new concept with the Ultra Ethernet Consortium. It's been around in academia since at least the late 2010s. And packet trimming is a kind of a simple concept. So when a packet shows up at a switch, I've got to make a decision of, do I forward it or do I drop it? And the decision of whether I forward or drop a packet is based on whether the destination queue that packet is going to is full. If the destination queue is full, I don't have any place to put it, so I have to drop it, right? And if it's not full, then I enqueue it in the destination. So packet trimming changes that a little bit. It's a little bit like ECN marking, wherein if a packet arrives and the queue is full, instead of dropping that packet, I'll truncate it. And I'll just reserve a little bit of bandwidth for packets that arrive when the queue is almost full. Or a little bit of queue memory for packets that arrive when the queue is almost full. And so with packet trimming, I'll take a packet and I will truncate it when it otherwise would have been dropped from, say, 4K down to 64 bytes. And then I'll mark it so that the end stations know that the packet was trimmed, was truncated. And I'll mark it by changing the DSCP value in the packet header. And then I will enqueue it in a high priority queue going to the same destination. And why put it in a high priority queue? It's because it delivers the signal sooner to the endpoint, which lets the network react more quickly. And so this is implemented in the switches. And so this is switch support for fast loss detection in this multipath environment. So packet trimming, like I said, it reduces packets from 4K down to 64 bytes. And this is a 2-scale picture of the difference between 4K and 64 bytes. But it's a substantial 64x reduction. So with a small amount of packet buffer reserved for trimmed packets, I can have an important impact on the transport protocol. Only packets that are trim eligible, which is indicated by a DSCP code, end up getting trimmed. And this is important because existing protocols will get very confused if you just chop a packet off and deliver it to the TCP stack. And then the trimmed packet signal at the end station, when a trimmed packet arrives, it allows the end station to slow down, to request retransmission, and it provides precise, fast loss detection in a transport protocol environment where packets are potentially delivered out of order. The third challenge associated with a packet spraying transport protocol is that, and really this is partly about packet spraying and just partly about the high bandwidth short RTT environments in which AI and HPC applications live, is that we would like a congestion control protocol, which is the part of the protocol that's responsible for determining how fast I'm sending at any given point in time, to get to wire rate very quickly. So AI and HPC applications can transfer a lot of data, but in some cases the data is only like a megabyte or 16 megabytes. At 800 gig, a megabyte of data takes 1 round trip time to deliver. So I can't spend, if I'm doing 1 megabyte or even 8 megabyte transfers, I can't spend many round trip times to figure out what the right rate is and slowly speed up so that I don't overload the network. I've got to start sending pretty much at wire rate if I want to be efficient. But if I start sending at wire rate, there's some chance that I was wrong and that there actually is congestion in the network. And in that case, I need to back off very quickly. There's no time. This is a TCP kind of slow start diagram here on the right, and I don't have, and that's that blue section there is showing TCP doing its slow start, which is actually exponential start. But I don't have time to wait for TCP to ramp up either at the beginning of time or whether it's TCP, this is Reno, or whether it's cubic or BIC. I don't have time for many round trip times to figure out what the right rate is. So we need a transport protocol that can ramp quickly and slow down quickly. But as I said before, it's losses, delays, ECN marks that traditional transport protocols depend on to figure out what rate is safe to transmit at without overloading the network. So the UET, the transport protocol of the UEC, needs new algorithms for this packet sprayed network. Existing algorithms are either too slow, depend on ordering, etc. So the Ultra Ethernet transport protocol has 2 flavors of congestion control that it's defining, and the 2 can either be used separate or work together. And there's a sender-based congestion control and a receiver-based congestion control. The sender-based congestion control is more like the way things work in TCP, where there are individual instances of senders that are all running their own congestion control algorithm, and it's a distributed algorithm. This is the picture on the upper right. So if I've got fan-in of multiple flows going to a single destination, the congestion control, the smarts, is really happening on the senders, and they're working together in a distributed algorithm to figure out that there's loss, to figure out that there's congestion, and then back off so that they're each sending at 1/nth of the rate to any given destination. And this algorithm uses delay, marking, trimming as well as indicators of congestion, and it's different from, it's inspired by much of the work in TCP congestion control over the last 25 years, Swift, DC TCP, others, but is tailored for the short RTT high bandwidth environment of AI and HPC applications. There's a second congestion control algorithm, which is kind of more different from what is typically used, which is a receiver-based congestion control algorithm. The receiver-based congestion control algorithm in the Ultra Ethernet transport, the way that works is senders send an indication to the destination host indicating, hey, I would like to send you some data. I'd like to send you a megabyte of data. And the receiver has global knowledge of everyone who's sending to that destination because everybody has to talk to it. and then it allocates credits to the incoming senders to say, okay, you can send me this much data now. There's n of you, so each of you can send me 1/n of a megabyte in the next round trip time. And so that receiver-generated credit mechanism does a really great job of managing incast, because like the receiver has kind of perfect knowledge of everyone who's trying to send to the same destination. There's also a mechanism for optimistic transmission before credits are received. So like I don't have to wait a full round trip time to start sending. But of course, in that first round trip time, I don't know how many other senders there are. So I have to make kind of a guess about how much data I can send. But both of these are new congestion control algorithms that control the speed of transmission that are designed to deal with a packet spraying and out-of-order transport protocol. So I want to talk about one other attribute of the Ultra Ethernet Transport Protocol, which is ephemeral connections. So the problem, again, we're trying to deliver, actually not tiny amounts of data, but as quickly as possible, so that the network doesn't end up the bottleneck in these distributed computations. So the picture on the left is just a picture of a traditional three-way handshake like TCP does, SYN, SYN-ACK, ACK. And data doesn't get transmitted in TCP until the SYN, SYN-ACK is complete. That is fundamentally slow. If I have a transfer that's only 8 RTTs or 1 RTT, I would prefer not to wait 1 RTT for a handshake to complete before I can send the data. So it's like eliminating, and what I want is really the picture on the right here on the slide, where I just start sending immediately. So that is what the Ultra Ethernet transport allows you to do. You can start transmitting immediately, and the connection is established on demand by the first data packet that shows up. There's an auxiliary benefit of doing this, which is that it saves state, because end stations are no longer trying to avoid the three-way handshake by caching connections. If I have a significant startup penalty for a new connection, then my response, in order to keep my application time, my application performance good, is to cache those connections. But the connection state for connections operating at these speeds has to be maintained in the network interface card, where state is expensive and limited. There's many of these, and it's running at very, very high speed. And so caching connections in the network interface card is expensive. So it's a big win if I don't have to cache those connections for good performance, and I can just spin them up on demand as packets arrive. And so that's what the Ultra Ethernet transport is enabling you to do, is to start a connection when the first data packet arrives. I start sending at wire rate, and that enables me to not keep connections around that I'm not using, and it saves state as well and reduces cost. So that's Ultra Ethernet transport protocol. I want to look, I showed you 4 layers. I want to look at some of the activity that's happening at some of the other layers, application, network, and link layer specifically. So the Ultra Ethernet transport is built on top of a new API that is libfabric. Libfabric is not a new API to the world. It's just new to Ultra Ethernet, which is also new. So libfabric is a API that's been a long-standing API. It's standardized by the Open Fabrics Alliance. There's a 2.0 version of libfabric that's out there, which the Ultra Ethernet Consortium is standardizing on. And it's really like libfabric, if you don't know what it is, it's sort of a modern API for network-based applications, but it goes beyond what kind of sockets does, which is just sort of send and receive. So it's got support for constructs and primitives that are important for good performance in HPC and AI applications. So remote memory access, placing data directly, specifying buffers that indicate where data can be directly placed, tagged messages, messages that are sent with a virtual identification of where they're going to go, atomic operations like increment, decrement, atomic replace, compare and swap. And then support for collective operations are in the protocol. I talked a little bit about collectives, broadcast, all reduce, scatter gather, that sort of thing. And then queued notifications, asynchronous notifications, which are prevalent in AI and HPC applications today, like the Verbs API, which is kind of the prevalent API for RDMA today. This is widely used, but this has a renewed version of it. So libfabric is kind of a new API for HPC and AI, and the Ultra Ethernet Consortium is doing a number of things. So we adopted libfabric 2.0, which is the latest incarnation of the libfabric API, and then we're extending it in a few small ways for concepts that the Ultra Ethernet has that just weren't there or weren't well supported by the existing APIs. We're building a libfabric provider, which is kind of a plug-in to the libfabric's code, like there's code from the Open Fabrics Alliance that you can get, and there's sort of a plugin that maps the generic APIs onto the Ultra Ethernet transport. So like you issue some API call and it creates, just in the same way that you open a connection and it creates a TCP connection under the hood, this does the same thing. It's just creating a Ultra Ethernet transport session and using that and configuring it. And then the Ultra Ethernet will be making contributions of code to OFI, like in particular a reference provider, a reference implementation that vendors can pick up. And the people will have, because so much of the Ultra Ethernet transport is implemented in the NIC hardware, there will be proprietary, each vendor will probably have some part of the libfabric stack that they provide, but there's a reference provider that, like the Ultra Ethernet Consortium will build, that other people can build on if they're building their own NICs, so different NIC vendors can pick that up. Security, I mentioned this. This is kind of at the lowest level of the transport protocol, but this is kind of, in IP, this is IPsec, and in, web applications, it's TLS, and it's in the transport protocol. So the UET security kind of sits somewhere in between those two. Here's a picture of the header fields, if you want to like zoom in. It's a snapshot of the spec. But the Ultra Ethernet transport solution builds on the core principles of security from IPsec and PSP. If you're not familiar with PSP, it's a kind of modernized version of secure transport that Google has standardized. But it's things like, it uses AES GCM for the encryption cipher suite. There's key derivation functions that are used, initialization vectors. There's support for key rotation, anti-replay mechanisms, all of the security stuff that you would expect, but it's taken and designed for high-scale, both group and client-server communication. It also includes a model for host-level security, which is a little bit unique, in which the NIC can help enforce and prevent spoofed applications from pretending to be a different application on the same server. And this is integrated in the transport, so it provides confidentiality, authorization, authentication, not just for the data flowing over the connection, but also for the connection set up and tear down messages in the protocol itself. So it's integrated with the protocol stack. One unique aspect of the Ultra Ethernet security solution that I think distinguishes a little bit from IPsec or PSP is it's focused on these kind of distributed computations and group applications where I might have 128 or 256 GPUs all working together on some distributed computation. And these things all fundamentally, they're all part of the same application at some level, and they trust each other, right? And they need to trust each other. So in that environment, we're providing a security solution that does group keying, which basically makes rekeying, keying, the amount of key state one has to store reduced for these group applications. It's just like less expensive. In these environments, members kind of fundamentally trust each other, so we're providing efficient security for groups that's integrated into the transport protocol. I said that we're not touching Ethernet, which is 100% true. You can be a completely compliant Ultra Ethernet switch without doing anything new. But the Ultra Ethernet Consortium is extending the link layer optionally, which can help in some of these environments. So the thing I'll talk about is link layer retransmission. It is exactly what it sounds like. Link layer retransmission is addressing the fact that in a AI or HPC data center with many GPUs. I might have 10,000 or like 100,000 GPUs, like Elon Musk is talking about 100,000 GPUs or more, and Meta's out there talking about hundreds of thousands of GPUs that they're going to have by the end of the year. So if I have 100,000 GPUs in a 2-tier network, I have 400,000 transceivers, 200,000 links. Like, it's almost a virtual certainty that at any given point in time, one of these links, or many of these links, is not working perfectly. Like, links fail over time. Individual links and individual transceivers are very reliable and might have 5 years of MTBF or more. But if I have 100,000 of them, failures are happening fairly regularly. And these failures can impact application performance, in this environment where the performance of the entire computation is driven by the performance of the worst link in the whole computation, right? Remember that ring diagram. So LLR is a kind of local repair technique that tries to avoid end-to-end retransmits for cases where I might have a flaky link that is dropping packets more than I would like, but maybe not so bad that it's completely taken out of service. So the way that link layer retransmit works is there's an LLDP negotiation between link layer neighbors, between just an Ethernet peer and its immediate neighbor, that turns it on. Packets, when they get transmitted, are stored at a very low level in the MAC. So they're recorded in the MAC until either an ACK or a NAC is received from the other side of the link. On an ACK, the packet is tossed. The saved copy is tossed. On a NAC, it's retransmitted. And then the ACKs and the NACs are actually happening at the 802.3 PCS layer, at the Ethernet layer, at a super low level. So the retransmissions are very fast, just happening in hardware at the MAC. And this is an extension to 802.3 with these things called O codes at the PCS layer. The last bit of Ultra Ethernet functionality that I'm going to talk about, and this is addressing something that's a little bit farther out. It's in-network compute. And this is doing basically math in the network. So this is switch level support, like in the switch, direct support for collective operations, like all reduce, broadcast, all gather. If you remember, like the active networks buzz in like DARPA, in the 90s, this is kind of that come to life to some degree. But it's networks actually participating in the computation itself. So the way this works is there's a bunch of end stations, like GPUs, that are participating in some collective operation, like an all reduce, which is computing an average of a bunch of vectors, and each GPU has some vector of like 100,000 elements in it, and I want to compute an element by element average of all these. So the application says, hey, I would like to build a tree that can do an average. And it goes out and talks to the switches and builds a tree, which is this like red structure overlaid on top of the network. And then that red structure is configured, and then the end stations use a simpler version of the Ultra Ethernet transport protocol that's optimized for just like point-to-point operation. And it has to be simpler. It really benefits from being simpler because the switches are implementing many copies of this in hardware. And so it's expensive if you did the full transport. You don't need the full transport protocol. And then APIs kind of coordinate the building of the tree and the tearing down of the tree and the delivery of the data. And so this is something that's been done in proprietary implementations today, but this is the first time that it's actually being standardized. And so now we're standardizing it to operate with the Ultra Ethernet transport. And this saves both bandwidth and latency, and can be, we think, especially going forward, looking a couple of years out, this will be an increasingly important capability to have for some applications. Okay, so that's covers what I wanted to talk about where the Ultra Ethernet Consortium is at today. The work of the Ultra Ethernet Consortium will not end when the 1.0 spec is released, hopefully first quarter of next year. There's active work happening on the left column here in storage, mapping storage protocols on top of Ultra Ethernet. There's managing Ultra Ethernet endpoints and switches with OpenConfig and new Redfish models. Compliance and testing that will help us define test suites to tell if you're compliant with Ultra Ethernet. Performance and debugging of these applications, some tooling. There's some really interesting work in telemetry around CSIG and back to sender notifications that will be, I think, really, really powerful for a next generation of congestion control protocols and also for network visibility and performance debugging, which is like a non-trivial problem for these large distributed computations to figure out what is slowing it down and where are things being slowed down. A little bit farther out on the roadmap for the Ultra Ethernet Consortium is looking at programmable congestion control, which is defining primitives in the end stations that would allow more innovation in the congestion control algorithm. Alternate topologies. The focus of the Ultra Ethernet Consortium is networks that are a clove fabric or leaf spine fabric, like the ones I showed you. But there are people already deploying and have interest in alternate topologies like Dragonfly or Dragonfly Plus, whatever XFly is the flavor of the day, that are interested in mapping onto those topologies. And that requires new thought about the congestion control algorithms. The in-network compute, there's more work that could be done. This is just what's been done so far is just a stepping stone. And then I think it's inevitable that Ultra Ethernet will need to be thinking about applications that span more than just one data center, where the transport protocol is spanning across regional networks, across metro networks. Like the power of these data centers is so large that I can't put all the GPUs I would like to focus on one of these problems in one place, just for power reasons, for reliability, fault tolerance, disaster recovery reasons. Applications will end up being more distributed. So I think there's work to be done there. And then there are some people, like I said early in the talk, that are interested in not just interconnecting GPUs, but is there an application of some of the technologies that we've built for the scale-up network inside the node? Could we be using Ultra Ethernet there? So in summary, okay, just like trying to put this in context for NANOG. Data, like how is this relevant to you all and what y'all do? Like data centers aren't isolated. They will be interconnected. What I've shown you is what an increasing number of the endpoints and important endpoints in the data centers will be doing. These applications, like I said, will inevitably spread to metro networks, regional WAN networks, which is more traditionally the domain of NANOG. Large flows, high bandwidth applies there. And just like AI, these AI and HPC applications are like an important class of new applications that I think is just like y'all should know about. And I'm sure many of you are well aware of them already. But in terms of like a call to action or, for NANOG, what can you do here? I mean, I think we need your vision, your knowledge, your years of wisdom to understand what problems this will bring, what the next round of problems is coming, and then creative solutions that we haven't thought about, that you have thoughts about. Super interested in leveraging the wisdom and the experience of the NANOG community on the next round of problems. So in conclusion, for AI networks, the Ultra Ethernet Consortium and the Ultra Ethernet solution is very focused on providing application support for AI and HPC and RMA specifically on top of Ethernet. We're really committed to the view that Ethernet and IP can and will be supporting the critical needs of AI and HPC in the future. It's proven to scale. And we really think that Ultra Ethernet is the solution for AI and HPC of the future. So please, I hope this was interesting. If you found it interesting, join the Ultra Ethernet Consortium and help shape the future of AI and HPC networking. Thank you. Okay.
Al, that was great. Thanks so much. And again, for all of you that are here, this is the future. It's going to be an NVIDIA killer. So we need to keep thinking about that, all right? So keep thinking about that. But don't sell your stock yet on NVIDIA, because it still could be good for another 6 months to a year, who knows. We have questions for Hugh, please, while he's up. I appreciate it very much.
Hi, I have a question online from Matt Pitak, who's unaffiliated. Good talk, Hugh. Thank you. Is LLR expected to function across long-distance WAN links as well, or is it aimed only at data center links?
Well, I think that's an implementation question of LLR. And so like LLR will work depending, I think it would work across WAN links. it is dependent on how much buffering you, so an implementation question about how much buffering you have in the sender. I need enough buffering to account for a full round trip time. And so I think it kind of comes down to that. If the WAN link is so long that it's 98% of the end-to-end, then you ask yourself, well, how much am I winning versus just waiting for an end-to-end recovery, but I can detect it. So I think it would work. I think I would expect that most implementations to begin with are going to be targeted at data centers.
Thank you.
Thank you.
Justin Ryron, Kentic. You mentioned if you do spraying of packets and you're not hashing them across the links, some challenges you're going to face with detecting loss and out-of-order packets, congestion, that kind of thing. How do you deal with the reordering of the packets on the other end? Like if I get packet 1, 2, 3, and 5, presumably now the end station, that server is going to have to wait for packet 4 to come in 10 milliseconds later and reorder those. So you're going to have deep buffers on the servers. Is that the implied solution to that problem?
Yeah, really good question. So I mean, I think that the reorder buffer is kind of the obvious solution, is to just hold the packets until they've arrived in order. And if one of them is dropped, I just can't deliver the out-of-order ones until the retransmitted packet shows up. I do 1, 2, 3, 5, and until 4 gets there, I just can't deliver 5. And so I think that's the sort of traditional simple solution. But I think going forward, the Ultra Ethernet Consortium is, if you back up and you say, like, what am I fundamentally doing? I'm transmitting a bunch of data from my memory into your data. Why do I need to deliver these in order? Just like a packet shows up, I tag it with a tag of like what buffer it's going into, and then I just deliver it straight into the buffer in memory whenever it arrives. Now I need to do some bookkeeping. I need to kind of maintain a bit set or something to bookkeep when packets got lost, and there's that whole question of how do I figure out what got lost and when the transmission is done, and that's kind of the art of the Ultra Ethernet transport, is you have to do all of that. But if I tag the packets, actually delivering them when they arrive out of order isn't a big problem for these kind of applications.
Yeah, thank you.
Yeah.
Hi, thank you for your presentation. One quick question: when we talk about the traffic, are we talking about the traffic during the LLM training, or are we talking about the usage of LLM, or both?
Well, so it's both. I think that LLM, so there's inference and there's training in LLMs, right? So I think you're referring to like usage, you're talking about inference. So training, I think, tends to be at some level more demanding because it's just much larger. I mean, you like read about it in like any news organization, 10,000, GPT-4 was trained on somewhere north of 10,000 GPUs for 3 months. And so it's very demanding on the network. The problems are larger. Inference probably has more over time, there'll be like more GPUs dedicated to inference. The inference problem is a little bit easier because it tends to be smaller, and because there's so many copies of inference, there's a lot of push to shrink it. So I mean, I think GPT-3 or GPT-4 even, the rumor is it's sort of like inference happens on somewhere between 8 and 32 GPUs. I mean, I don't know that anything's published, but like that's kind of the rumor. And so it's much smaller. Of course, models are getting bigger over time. There's like mixture of experts models that'll be bigger, and so like I think some of these problems will persist as and probably in the future as models get larger will span across multiple server nodes. So I think it's both, although I think the training is harder.
Okay, because one of them is real-time inference. The other one is semi-real-time or offline. So from that aspect, I was trying to say that to see which one is that, but you're saying there's both.
Yeah, they're both relevant, and inference it's transfers across many levels, and so latency can be a little bit more. It's latency. It doesn't tend to be latency of the packet individually, but latency of a transfer can be have a bigger impact.
Okay, thank you.
Yep.
Hi, quick question, and thank you for the great presentation.
Please, please give your name and your company affiliation.
Yingzhen Future Way.
Thanks.
My question is, you have this out-of-order delivery, also packet training. So at the receiving end, what if you receive 1, 2, 3, 4, 5, but your number 4 is trunked?
So I mean, the advantage of trimming, I mean, the same thing, well, the reason to do trimming is because I know immediately that the packet was dropped and that it's never showing up. I don't have to wait for a timeout. or wonder, is it coming just a little bit later because it was delivered out of order? Like as soon as I receive a trim packet, I can immediately take action on it. I can either slow down because I know that it was dropped. There's some queue somewhere in the network that's overflowed, or I can request a retransmission if that's the right thing to do in the transport protocol. But it like prevents the end station, the receiver, from having to guess, is it still coming or has it been dropped? So it just knows sooner that the packet was dropped.
But before your number 4 is retransmitted, you will have to hold the 1, 2, 3, 4, 5, right? Before you send it.
Well, no. I mean, that,
no?
to the question, to the earlier person's question, like 1, 2, 3, and 5, at least by the NIC, they just get DMA'd into their final location in memory. I can't tell the application that the whole buffer has been received until all of them are there. But the NIC is free to DMA them with direct memory access. The NIC is free to just stick it where it's going to go. And I can deliver it. I mean, the out-of-order delivery is not just as a network, but it pervades all the way into the application layer as well.
Yep.
Thank you.
Yeah.
Hi, Kelly Irwin, Alta Fiber. So just thinking about all of this, with it being AI, at what point, if you're missing a packet, does AI just say, this is what I think that packet would have been? And it just creates it.
Really good question.
Because, I mean, on the board, we're looking at 10 packets, but we're talking about hundreds and thousands of packets, right?
I mean, I think that there, I mean, I think that there are, real, algorithmic questions that like might have a bearing on the transport protocol. And, similar problems that are, I mean, just being able to ignore some packets that are dropped, like, yeah, maybe this is possible. I don't think the algorithms, to my knowledge, nobody's like experimented with it. I think there are problems similar to that people are looking at at a more macro level, which is what do I do when a single GPU fails? And I've got like 1,000 GPUs, part of some computation. Today, when a single GPU in a big distributed computation fails, like I'm stuck. Like I was depending on that, and so I have to roll back to a checkpoint, which might have been like an hour ago. And like that's really expensive. But like this is an algorithmic end-to-end application level fix. And so like you say, well, like I don't need to do that. Just keep going, right? And to your point, could I just keep going? And like, good point. So
like compressed graphics, right?
Yeah.
That's what we do. We're throwing out all this information because we can kind of infer it.
Yeah, and I mean, this is an application level fix that could have ramifications on the transport. So it's a good idea. I mean, join the UEC.
Hello. Oh my goodness.
Name, affiliation.
I'm Joel from MaxIX.
Thanks.
My question is, when this goes beyond the data center, you mentioned inevitably it'll go to Metro and WAN. Do you foresee the need for thousands of fibers connecting these Metro nodes?
Well, kinda. I mean, I think that the more bandwidth. So for distributed training, there is a significant tapering of the traffic at the today. There's commonly a significant tapering of the traffic toward the spine because I'm doing like this all reduce is the main, it's data parallel, so it's many copies of a model that are all operating in parallel, updating their weights, and then those weights all get averaged. And they can be sort of locally averaged within a network, and then those averages can get merged together. And so that's the gradient reduction step of a training algorithm. And so at some level you say, well, if that's how it works, like I don't need very much bandwidth between data centers at all. Except, well, like load balancing isn't perfect, job placement isn't perfect. People would like to distribute jobs across data centers, and then the applications are changing all the time. So like the application that's completely dominant for neural nets today is the transformer model. It's like almost everything is transformers today. Like it didn't even exist like 5 years ago. It's like completely new. So there's a sense that like things are gonna change. And so people don't wanna bake too many assumptions in the network today about like how it'll work in 2 years. So yeah, I mean like within the limits of your wallet, like yes.
Last question.
Yeah, I'm Tony from TD Bank. You mentioned protocol support for like IPsec and TLS. Is there a plan for native link level encryption?
Well, so I mean, I think link level encryption is kind of covered to some degree by the MaxSec. for most of these deployments. Like if people want to do like hop by hop link level encryption, like you can do MACsec today in products that support MACsec. I mean, MACsec, is a cost adder on any given switch. Like it takes some silicon area and real estate to implement MACsec in the end station. So it's not something that comes along for free, either in terms of silicon area or power. So that's a bit of a trade-off. But like that, from a solution standpoint, that absolutely exists. But people on top of MACsec want end-to-end encryption that sort of, I don't trust the net. There's the people who like don't trust the network in the middle, and they want end-to-end encryption. And so that's the solution that UEC is addressing. But I think there are people doing, protecting their infrastructure today with hop-by-hop encryption. So it's a very real thing.
Okay, thank you.
Thanks.
All right, Hugh, thank you so much.
Thank you,
Beautiful. Steve. Everybody, please, a warm welcome and thanks again for Hugh.